Thank you to invite me to give me a talk here. So the topic is about graph structures and well-quasi-ordering, and it's a joint work with my advisor, Robin Thomas, at Georgia Tech. Okay, so the talk contains two parts. The first part is about a structure theorem to exclude a fixed graph as a topological minor. And the second part is about well-quasi-ordering and the conjecture of Robertson. And it will be an application of the first part. Okay, so we say G contains an H subdivision, or we say G contains an topological minor isomorphic to H. If G contains a subgraph that can be obtained from H by replacing edges by internally disjoint paths. So we want to see what's the structure of the graphs that does not contain arbitrary fixed graph as a subdivision. So for example, if H is K33, then Dvoraks Theorem says that if the graph does not contain a K33 subdivision, then it should be a planar graph, or it contains at the most 5 vertices, or it has a vertex cut of size 2. Because 3-connected non-planar graph contains K33 subdivision. But how can we say about a general graph H? Give me a graph H. How about the graph do not contain an H subdivision? So something unknown, but in order to explain those theorems, we have to define a notion that's called tree decomposition. It gives a way to decompose the graph into small pieces, and these small pieces form a tree structure. So formally, we say Tx is a tree decomposition of a graph G. If I have a tree T, and every node of the tree associated with a subset of vertices of the graph G, and we call the subset associated with T is the back at T. And we require that the union of all backs contains all vertices of the graph. And we also require that for every edge of the graph, some back must contain the both ends of this edge. And the third one says, for every vertex phi, we see the node whose back contains this vertex. It must be connected. So it gives me the tree structure of a graph. And the width of the tree decomposition is the size, the maximum size of a back minus 1. The minus 1 is to make tree has a tree decomposition of width 1. Because if I have a tree, then I can construct tree decomposition. The tree is like the original tree, and every back contains each end of an edge. And the last thing we have to define is called a torso. So the torso of the node is a subgraph of graph G that induced by the back at T. And then we add edges such that the intersection of the back at T and the back at T prime induce a clique for every neighbor T prime of T in the tree. So probably I should draw a picture. So if this is my tree decomposition, and each vertex of the tree corresponding to a subset of the graph. So my graph could look like this. And this part is the back of this vertex. And this part is the back of this vertex, and so on. So this one is the back of this one, this back of this vertex. And the torso at this vertex just make everything here become a clique. So here are 3 huge cliques. Okay, so that's the torso. Okay, so now we can see the first structure theorem. The structure theorem is given by Robertson and Seymour. The theorem says, give me a graph H. What's the structure if a graph does not contain H as a minor? When H is a subcubic graph, then the minor is the same as subdivision. So it gives me the first structure theorem for excluding subdivision for subcubic graphs. So the theorem says that for every graph H, there are some constants A, B, C, such that every graph that does not contain an H minor, it has a tree decomposition such that every total is A, B, C almost embeddable in a surface in which H cannot be drawn. So I should tell you what this A, B, C almost embeddable means. It's pretty complicated. So we pick the surface sigma, like here, and we pick B cross disks in the surface. They are pairwise disjoint. So like these two parts, this disk and this disk. I have two disks here. I should pick B disks. And then I can draw the graph into this surface in this way. I first delete A vertices, and then I draw the remaining graph into the surface, such that I don't allow edge that has one end inside a disk, and the other one is outside the disk. And I don't have two edges cross unless they are in the vortex, they are in the disk. Furthermore, if we focus on the subgraph that will draw in the disk, it will have the tree decomposition of width at most C. C is the number C here. The number C here. And this tree decomposition, the tree is actually a path. And if we see the vertex draw around the boundary of such a disk, this is a cyclic ordering. And our tree decomposition, the kth vertex must contain the kth vertex drawn on the boundary. So such a subgraph drawn in the disk is called the vortex of depth at most C. So it's pretty complicated, but I cannot remove any words in this theorem. Removing every word from it will make it incorrect. And actually, this theorem is more or less a characterization, because if a graph G, let's satisfy the conclusion, means that if we have a tree decomposition such that every total is ABC almost embeddable in a surface in which H cannot be drawn, then it cannot contain a very large graph as a minor. So it's more or less a characterization. Okay, but how can we say about subdivision, topological minor? What's the structure? Graham and Marx first gave such a theorem. It says that if you give me a graph H, then there are some constants such that if G does not contain H subdivision, then it contains a tree decomposition such that every total is almost bounded degree. It means that it can contain some large degree vertices, but there are only bounded number of them. Or it can be almost embeddable in a surface of bounded genus. So here, there are two possible. The second possible is pretty similar as the previous structure theorem. But here, the genus of this surface could be large. It's not a surface that H cannot be drawn. But it gives us the first structure theorem for excluding a fixed graph as a subdivision. And recently, Dvoraks improved their theorem. They improved the second conclusion. It gives more structures information about the total when it's almost embeddable. It says that when the total is almost embeddable in a surface of bounded genus, such that if H can also be embedded in this surface, then there's a spatial value MF is at least 2. I'll define it later. So there's a spatial value at least 2. And such that for every vertex of large degree of the total, it must be containing a vortex. And there are at the most MF minus 1 vortices contain such a vertex. So first, let me define what's the number MF. MF of H sigma means it's the minimal number of phases incident with vertices of H of degree at least 4 among all possible embeddings. So we draw H in sigma in a regular way. I don't want H's crossing in sigma. So I draw H in sigma in some way. And there are many degree 4 vertices. And I compute how many faces I should touch all degree 4 vertices. And then I pick the minima. This is the number MF. So what does the theorem say? The theorem says that, okay, now I have a total that is almost embeddable in a surface sigma. And there are two possible. Either H can be drawn in this surface sigma, or it cannot. If it can be drawn in the sigma, then I can make the large degree vertices more concentrated than H, right? Because I somehow only need MF minus 1 faces that incident with large degree vertex. But for H drawing the sigma, it needs at least MF, this number of faces, to touch them. So it's pretty good. It gives somehow a more structural information about the theorem. But let's go back to the first one. How can we say about the first one? It says that the total contains bounded number of vertices of it has bounded number of vertices of large degree. But how do we mean the large degree? I mean it's larger than constant, capital D. And this number only depends on H. But it could be much larger than the maximum degree of H. And it's also obvious that we cannot improve this number D to be smaller than the maximum degree of H. Because every graph whose maximum degree less than the maximum degree of H cannot contain an H subdivision, but it can have arbitrary many vertices. So this capital D should be at least the maximum degree of H. So how can we say, can we improve this number to be the maximum degree of H? So that's my question. And the answer is yes and no. We can improve this number to be the maximum degree of H, but we cannot state the theorem in this way. We should state it in terms of Tango. I'll define Tango later. So before to define the Tango, we say AB is a separation of a graph G if AB are a pair of H disjoint subgraphs such that the union of them is a whole graph. And the order of this separation shows the number of common vertices. And the formal definition of a tangle is a set of separations that satisfy some properties. So before to say this, let me tell you what's the intuition of a tangle. So first we see a highly connected subgraph. If I have a highly connected subgraph, and I cannot separate this highly connected subgraph into two pieces by a separation of small order. So the highly connected subgraph must contain in one side of the separation. Either it's in the A side or in the B side. So it tells me which side of the separation is the important side, or I call it the big side. And Tango does the same thing. Tango contains a set of separations, and it tells me which side is the important side of each separation. Okay, so let's see the formal definition. We say a tangle in a graph G of order theta is a set of separations of G of such that for every separation AB of order less than theta, either AB is in the tangle or BA is in the tangle. And if AB is in a tangle, then I say B is the big side of the separation. And if BA is in the tangle, then the A side is the big side. So it tells me that for every separation of small order, one side should be a big side. And the second condition says that if I have three separations in the tangle, then the union of small sides cannot be the whole graph. So the small side should be small. And also, if I take A1, B1 be AB, and A2, B2 be BA, and A3, B3 be anything, then it tells me that I cannot have AB in the tangle and BA also in the tangle, because otherwise A union B will be the whole graph. It will be a contradiction. So it tells me that there's only exactly one side is the big side of each separation. And the third condition of the tangle just says the small side should be small. The small side cannot contain all the vertices. So the tangle is more or less a highly connected subgraph because they have the same behavior. They can tell me which side of a separation is a big side. And on the other hand, let's go back to tree decomposition. If I have a tree decomposition and they have a bag of large size, what does it mean? It means that I cannot separate this big bag into two pieces by a small separation. For otherwise, I just separate and make the bag smaller. So, in a tree decomposition of small width, of minimal width, every bag of large size corresponding to a highly connected subgraph. And the other hand, you can think it corresponding to a tangle. So that's the intuition of the tangle. Okay, and one more definition. I say a vertex is k-separable from the tangle if there's a separation in the tangle of order at the most k such that this vertex is in the small side, strictly in the small side of the separation. So if you think tangle is a highly connected subgraph, then this definition is pretty natural. Okay, so now we can state our theorem. This theorem says that give me any number d and h. D should be at least 4, but it's okay. Such that there are some constants such that for every graph h on h vertices of maximum degree d, and if G does not contain an h subdivision, then for every tangle of large order, I can find bounding number of vertices such that either I delete those bounding number of vertices, every remaining vertices should be d minus 1 separable from the tangle. Or, after I delete the bounding number of vertices, I can almost embed the graph into a surface of bounded genus. And such that if H can be also embedded in this surface, then MF is at least 2. And for every remaining vertex that is non-d minus 1 separable from the tangle, it must be containing a vertex. And there at the most MF minus 1 vertices contain such a vertex. So the second one is pretty similar as the Dvoraks Theorem. But here we replace the degree by the d minus 1 separable condition.
What is T minus Z?
T minus Z?
Yeah.
Okay, so it's a good question.
Vertex from tangle?
Yeah. So T minus Z, formal definition is this. A minus Z, B minus Z for every AB in the tangle. Yeah, I'm supposed to not to tell you this because it will make more complicated. But so intuitively just said I can delete bounding number vertices and separate the vertex from the tangle or the highly connected subgraph. Yeah, so for a large degree vertex, it is not clear whether it can be separable from the tangle by a separation of small order, right? But this theorem says I can separate every vertex by a separation of a separation order at most d minus 1. So more or less, the tangle does not contain a large degree vertex. Right? If you think tangle as a subgraph, and this language tell you every vertex in this connected subgraph, it cannot have a large degree vertex. Yeah. So that's why I said I can replace the number capital D by the maxima degree D. But this theorem is stated in terms of Tango. It's not same as before.
But this graph might still contain H, right? I mean, inside G you might have
An H subdivision? You mean?
yeah, like
You mean if G satisfies this conclusion, can it contain the H subdivision?
Right.
Yeah, it could. It's like the structure theorem of Robertson and Seymour.
Alright.
Even though you satisfy this condition, you can also contain an H minor. But you cannot contain a very large graph as a minor. And here's the same. If you satisfy this condition, you cannot contain a very large graph as a subdivision. Yeah. Okay, any other questions? Okay, so let's see a corollary. How about H is the outer planar graph? What does it tell me? If H is the outer planar graph, then H can be embedded in every surface with MF equals 1, right? Because every vertex is incident with one face. So MF is 1, at the most 1. So it means that the second condition cannot hold. Because second condition says if H can be drawn in this surface, outer planar graph can be drawn in every surface. But it cannot have MF at least 2. So I don't have the second condition. So it means the first conclusion always holds. And this would be a very important observation for the second part. Okay, so now we go to the second part. It's about Well-Quasi-Ordering and the Robertson's conjecture. So what's a Well-Quasi-Ordering? A Well-Quasi-Ordering is a reflexive and transitive binary relation such that every infinite sequence contains an increasing subsequence. And one application of it is that we can characterize a property by finitely many elements. So formally, if a property is closed under a relation, means that if an element B satisfies this property, it implies that every element A satisfies this property for every A less equal to B under this relation. So it's closed under this relation. Furthermore, if this property is a Well-Quasi-Ordering, and the property is closed under this Well-Quasi-Ordering, then there must be a finite subset Y of X such that every element X satisfies Y if only if it's not greater or equal to an element small y in the finite set. So the proof is easy. We just pick the minimal element that does not satisfy the property Q. Because it's Well-Quasi-Ordering, I cannot have infinitely many minimal elements. So this means the minimal elements are finite. So let's just set Y, and we just check whether this element contains a minimal counterexample. Not minimal counter, minimal elements that does not satisfy this property. Yeah. Okay, so it means I can characterize the property by finding many elements because I just test whether the element is greater or equal to any minimal elements not satisfy this property. And it also gives me an application in algorithms. Because if I can test any two given elements, x, y, whether x less equal to y in polynomial time, then I can test this property in polynomial time. Because the set y here is finite. The number of the size of y only depends on this property q. So fix this property. Y is fixed. And I just test, you give me an input x, I just test this property finitely many times. This number only depends on property q. So it gives me a polynomial time algorithm. Okay. So the Well-Quasi-Ordering is pretty strong. It gives us the existence of an algorithm, even though it doesn't give a constructive way to give the algorithm. Okay, let's see some example on graphs. So graph minor theorem of Robertson and Seymour says that graphs are well quasi-ordered by the minor relation. It means that if you give me infinitely many graphs, one graph should contain another as a minor. So apply the theorem in the previous slides. It says that every minor cross property can be characterized by finitely many elements. So for example, I fix a surface, and the property Q is that whether this graph can be drawn on this surface. It's a minor cross property, because if the graph can be drawn in this surface, then every minor of it can also be drawn in it. So it's a minor cross property. And this theorem tells me that for every surface sigma, I have a finite list of graphs such that the graph can be drawn on this surface if only if it does not contain any graph in the list as a minor. Okay, so it's one application of it. And also, Robertson and Seymour proved that if I fix the graph H, test whether G contains H as a minor can be done in polynomial time. So also apply the statement in the previous slides. It says every minor cross property can be tested in polynomial time, even though we don't know the algorithm, but the algorithm exists. So it's pretty strong. I don't have to know what's the property. I just know that if it is minor cross, then it must have a polynomial time algorithm. And actually, the running time is not bad. It's like n to the cube. So it's not that bad. Okay, so that's the application of Well-Quasi-Ordering. And besides of the graph theory, besides the graph minor theorem, Robertson and Seymour also proved the other Well-Quasi-Ordering result in graph minor series. They proved that graphs are well-quasi-ordered by the weak immersion relation. Weak immersion relation is similar as topological minor relation, but let me formally define it. If G contains H as a weak immersion, then G contains a subgraph that can be obtained from H by replacing edge of H by H disjoint path. For topological minor, the edge are replaced by internally disjoint path, but here we only require the H disjoint path. And Robertson and Seymour also proved that graphs are well-quasi-ordered by the weak immersion relation. So now it's H natural to X. How about the topological minor relation? Because their definitions are pretty similar. How can we say about this? And because for subcubic graph, we know that the minor relation, topological minor relation, weak immersion relation are all the same. So we know that subcubic graphs are well-quasi-ordered by the topological minor relation. But how about a general graph? And the other stuff is known. Kruskal proved that trees are well-quasi-ordered by the topological minor relation. And Nash-Williams gave a shorter proof of this theorem. And his proof is important in our application. Okay. But how about a general graph? General graph can be well-quasi-ordered by topological minor relation? Well, actually it's not. It cannot be true. So here's an counterexample. In this infinite sequence, we see the kth graph of this sequence is obtained from this way. We pick a path of length k and duplicate each edge. And then we attach two leaves to each end of the path. So in this sequence, no graph can contain another as a subdivision, because no graph can contain another by replacing edges by internal disjoint paths. Right. So it's a counterexample. No graph can contain another as a subdivision. So the topological minor relation does not well-quasi-order graphs. Okay, but what's the obstruction in the previous example? Let's first see a graph that we call a Robertson chain. A Robertson chain of the length k is a graph obtained from the path of length k and duplicate each edge. So this graph is a Robertson chain of length k. So in the previous counter example, we can find arbitrary long Robertson chains, right? Because the kth graph contains a Robertson chain of length k. And Robertson conjecture that, how about if we exclude the long Robertson chain? If we fix the positive integer k, the graph with no topological minor isomorphic to a Robertson chain can be well quasi-ordered by a topological minor relation. So is the conjecture clear? And the answer is yes, we can prove that. It's our second main result. So if we fix the length of the Robertson chain and graph does not contain the Robertson chain as a topological minor with length greater than this, then the graphs are well quasi-ordered by a topological minor relation. And the proof of this theorem is pretty long and pretty complicated. So we just state the ideas of the theorem, how we prove that, and explain the tools we developed in the proof. So the idea to prove this theorem is to use the minimal base sequence argument. It's pretty similar as Nash-Williams' proof of Kruskal's theorem, that trees are well quasi-ordered by topological minor relation. So to do this, we have to encode our graph into trees. And then we can use a similar argument. So because I want to encode a graph into trees, I need a nice tree structure. And also I need some structure theorem to exclude Robertson chain to give me more structural information. Okay, so
are you using the classical graph minors theorem as part of?
I use a lot.
Yeah, okay. Yeah. I just wanted to make sure it's not building it from scratch.
Yeah.
Okay.
So I not only need graph minor series, I have to improve some results and use lots of theorem. You will see later. Yeah. Okay, so the tree structure we will use is tree decomposition. And tree decomposition is defined in the graph minor series. So we will use the same tool here. So we will encode our graph into trees by using tree decomposition. And the key idea of Nash-Williams' proof of Kruskal's theorem is that trees has two nice properties. One property is that if I know that I have many graphs, each of them is a forest. So for example, it's the first graph, and here's the second graph, and so on. If I know that if you give me such an infinite sequence, and I know that this sequence has an increasing subsequence, then this sequence means I add a vertex adjacent to the roots of each subtree. Then in this sequence, the graph also well quasi-ordered. I mean, it contains an increasing subsequence. So it somehow means I can first forget the roots and see the remaining graph. If they are well quasi-ordered, then the original set are well quasi-ordered. So this is the first property. The second one is that I need that if the tree is a rooted tree, here's a root. This subtree must contain every subtree as a topological minor. It's pretty clear, right? It's a subgraph, and I just need a path to link the nodes of the trees. So the tree has these two properties. Okay, so I also want the same property here. So here is one of them. So first I need a definition. For every tree node T, I write g to the t be the subgraph induced by the union of bags at the t and its descendants. So for example, if this is my tree decomposition, and it's a node t, then g to the t is the subgraph induced by the bag of these subtrees. It's g to the t. Okay. And I hope that if I have two nodes, one is P, one is D, and the P is the ancestor of D, then, and if they have the same size of their bags, I hope G to the P can contain G to the D as a topological minor. And I hope the phrases in the descendant bags are simulated by phrases in the descendant of the ancestor bag. So let's see an example. So I have two nodes, P and D. P is the ancestor. And the bags associated with these two nodes have the same size. And if I have an extra condition that for every vertex in the bag at the D, there's only one edge incident to each vertex, like this. And suppose that I have disjoint paths from the bag of P to the bag of D. Then I can have this property. You can see that if I mapped the vertices in the bag of D to the vertices in the bag of P with the same color, then G to the P contains G to the D as a topological minor, right? So the vertices map to the vertices there. And because I know there are only three edges here, each vertex is only incident with one edge. So I can use this red disjoint path to simulate those edges. So in this case, I have this nice tree structure. Yeah. And also in this case, what do I want? I want every vertex only incident with one edge. So actually, this bag of the tree decomposition is not a vertex cut. It's a vertex cut, but it's also an edge cut. If I delete these three edges, then I can separate the graph into two pieces. The edge cut has the same size as a bag. So I hope I can convert the vertex cut of the tree decomposition into edge cuts. Okay, but actually I cannot do this. I cannot convert all vertex cuts into edge cuts. But it's good enough if I can convert some of them, such that if I see those bags that are corresponding to edge cut, and I delete them, I get many components of the tree. If each subtree has bounded height, then I can do induction on the height. And then I merge all subtrees into a new bag. And then in the end, the tree decomposition, every bag corresponding to a edge cut. Okay. And also on the other hand, I can prove that if I have a tree decomposition and I have many disjoint bags, then I must be able to find the edge cut between those bags. Otherwise, I can construct arbitrary long Robertson chain. So I know that if my graph does not contain a long Robertson chain, there must be an edge cut between the bags in a tree decomposition. So I want to insert these edge cuts into the tree decomposition. But however, I cannot just insert the cut because the cut in the tree decomposition is a cross-free family. So if I insert a cut, then I have to uncross the cuts to maintain the tree structure of a tree decomposition. So that's bad. I cannot just insert every edge cut I want. But our strategy is that if we start with a tree decomposition, let's already realize sufficiently many cuts. Then the process inserting edge cut doesn't impact the tree too much. I don't lose too many edge cuts. It's my, yeah.
So, is this the main place where the Robertson chain occurs in your curve? Or is this sort of the
That's the first step. Yeah.
But it does occur in, I guess I'm sort of wondering how unique this Robertson chain is.
Because during the counterexample, you see many Robertson chain, right?
Yeah.
So I want to see if I don't have Robertson chain, what can I have?
Sure.
Yeah. And also I need a nice tree structure to do well-quasi-ordering. I want to encode our graph into trees. And I show you that I hope I have edge cuts. And the very lucky is that if the graph does not contain Robertson chain, then it must have many edge cuts. So I want to use these edge cuts. Okay, so I want the tree decomposition. They realize very many cuts. So we developed a new kind of tree decomposition. We call this strongly linked tree decomposition. So what does it mean? W is an integer. A tree decomposition Tx is W strongly linked if for every two nodes of the tree, T1 and T2, T1 and T2 could be the same. And for every two subsets of the bag at T1 and T2, so I have two subsets Z1 and Z2. Each of them is contained in XT1 and XT2, the bag at T1 and the bag at T2. And these two sets have the same size. Z1, the size of Z1 equals the same size as Z2. But the size is at most W. Okay, and if I know that there's a separation of order at most the size of Z1, separating these two sets, Z1 and Z2, then I must be able to find a bag realize this kind of separation. It means that I can find a node T that is in the T1, T2 path in the tree. And the size of the bag at the T is at the most the separation separate Z1 and Z2. So if you are familiar with tree decomposition, there's an old notion called linked tree decomposition. In that case, it does not allow the separation has order equal to the size of Z1. It should be less than the size of Z1. But for strongly linked tree decomposition, we can allow the order equals the size of Z1. So every strongly linked tree decomposition is a linked tree decomposition. It's a stronger property. So you might ask whether do we ask too much? Does the strongly linked tree decomposition can exist or not?
I mean here the W is
any number.
Constant, right?
Yeah,
so
some constant. So you for every graph G there's a
if W is smaller, then this doesn't imply the linked tree decomposition.
yes, but if you take W to be the number of vertices, then it implies it. Yeah. Okay, so it's a theorem. Give me any number h. Every graph has a h strongly linked tree decomposition of adhesion at most h. And if h is at least the tree width of G, this strongly linked tree decomposition has width equal to the tree width of the graph G. And if the graph G does not contain a Robertson chain of length greater than k, then this tree decomposition has bounded height in terms of the length of Robertson chain and the number h. Okay, so if we use this tree structure, we are able to prove Robertson's conjecture for the case of bounded tree width. So fix every k and w. Graphs of tree width at the most w with no Robertson chain of length at least k as a topological minor can be well-quasi-ordered by a topological minor relation. Because, as I said before, I need two properties. The second one is by the H-cut property. The first one is automatic when the case of bounded tree width. I don't want to say the detail, but it's automatically. So I know that for every graph of tree width at most w, I have a w strongly linked tree decomposition. So I have these two good properties. So they can be well-quasi-ordered by some argument. Okay, so now we are done for the bounded tree width case. So now we have to focus on the graph of large tree width. And I told you before, if we see a tree decomposition that's minimal width, but then have a bag of large size, then I have a tangle of large order. So I must to be able to see what's the structure if I don't have Robertson chain, but I have large tangle. So here's a structure theorem. It's a corollary of our previous structure theorem. Because Robertson chain is an outer planar graph. So as I mentioned before, I only have the first conclusion. It says that if k is a positive integer, then there's some constant such that if the graph does not contain Robertson chain of length k, it's a topological minor. Then for every tangle in the graph G of large order, I can delete bounding number vertices such that every remaining vertices is 3 separable from the tangle. Okay, so now I can tell you a fake proof of Robertson's conjecture. So we know a tangle is more or less a highly connected subgraph, right? So we pick a tangle, we pick a highly connected subgraph. And for each vertex of large degree, I can find a separation of order 3, at most 3, to separate them. So I have a large degree vertex. Here's a tangle. Then I have large degree vertices. And I can find the separation of order at most 3. For each large degree vertex, I have a separation. Right? And if I contract the small side of each separation into a vertex, then the remaining graph is subcubic graph. Right? Because if I contract it, then there's only 3 neighbors here, 3 neighbors here, 3 neighbors here. So it's a subcubic graph. And we know that the minor relation, topological minor relation, Wigner relation, are all the same for subcubic graph. So the problem is reduced to the graph minor theorem. But it's not true actually. What's wrong here? I cannot contract each small side of each separation because the small side may overlap for different 2 separations. So I hope these separations could be cross-free. So in other words, I need a star decomposition. It means a tree decomposition, but the tree is a star. Or if we use the language in graph minor series, I need a location. The location is a set of separations such that the small side of each separation is containing a big set of other separations. So A is containing B prime for every 2 different separations, AB and A prime, B prime. So a location is equivalent with a star decomposition. If I have a location, then I have a star decomposition such that the back of each leaf is a small side of each separation in the location. And conversely is true. If I have a star decomposition, then I have a location such that each small side is the back of a leaf in the star. Okay, so I hope I can have a cross-free family of separations. So I need a location. And here's the structure theorem. So for every length k, there's some constants such that if a graph does not contain the Robertson chain of length k as a topological minor, then for every tangle of large order, I can delete bounding number vertices such that there's a location in the tangle satisfies some properties. There are 2 kinds of locations. The first kind is like this. Every separation has order at most 3. And there are at most 3 edges between the small side and the other side. So the separation just looks like this. Order 3, but I need 3 edges incident to them, so it must kind of look like this, and so on. And I have another type. It's more complicated. So in this case, the graph can be almost embedded in the surface of bounded genus as before, like this. So if you see this picture, you can see the location. So each blue area is a small side of a separation, right? So there are 2 kinds of separations. The first kind is same as before. It has order at most 3, and there are at most 3 edges between the small side and the other side. And the other kind is a vortex. The vortex has some property. It can be partitioned into many sets. And if we see the edges between two different parts, for example, for these two parts, there are 3 edges between them. Right? And for these two parts, we also have 3 edges between them. Actually, for each 2 consecutive parts, the number of edges between them are the same. That's one property of this vortex. And actually, I can find disjoint cycles passing through the edges between the parts. So what does it mean? It more or less says that if I have a vortex have this property, then I don't really need to know what's the property inside here. I can just encode the information into some vertex on the boundary of the vortex. It's complicated. I cannot say more stuff about it, but this property give us a way to encode the information. Okay, so now we are almost done. We can prove Robinson's conjecture in this way. We pick an H-strongly linked tree decomposition of boundary height. We know that this tree exists, but it has a large tree width. So some back has a large size. So we know that it corresponds to a tango. And we know that for each tango, I have a location that satisfies some nice properties. So I want to insert this location into my tree decomposition. And we can prove that after we insert it in some way, and then the optimal tree decomposition still have boundary height. And each back or large size realize a nice location. It means the location, but it has some nice properties, as we mentioned in the structure theorem. So that we can use Robinson-Simons theorem to prove Robinson's conjecture. So for the first location like this, we know each separation has order at most 3, right? So we know it's the location. We can contract each small side of the separation to get the subcubic graph. Then we reduce the problem to subcubic case. Use the weak emergence theorem or Griff-Minor theorem. So this type is okay, but this type is complicated. So we have to use another kind of relation. It's called a linear inflation relation. It's kind of a minor relation, but it addresses more information for a graph on a surface and more information about a vortex. It's also proved in Griff-Minor series, but it's pretty complicated. But we know we have a nice location and we have a nice vortex, so we can somehow encode the information into the vortex and reduce the problem to use a linear inflation relation. So we are done because we can deal with all kinds of locations. So we prove Robinson's conjecture. For every integer k, graph with no topological minor of length at least k isomorphic to a Robinson chain are well quasi-ordered by topological minor relation. Okay, so that's it. Thank you.